implementation. So at first, when you talk about graphs, the typical example are social networks, and this is also the example that we choose. In that case, it's the social network of orgs. So each vertex here represents an org, and the relations between them is a handshake, so they hate each other. And smart analysts would ask something like, who are the closest enemies of each org? So that's a typical question in an analytical scenario. And if you want to express such a question in the system, you could do it, for example, with ApacheFlink, Cypher, and then you had a query like this. So we have a match path, there is an org, which hates another org, and there are one or two hops between them, so one or two matches. Okay, let's have a look at this, how this would be looking like in Flink Jelly, which is the graph processing framework on top of ApacheFlink. So this is the same. It is exactly nothing, but it's expected to be nothing, because a lot of code they express the exact same thing. Even when you zoom in, so what's happening here is messaging between vertices. Here we have something like a hate label, like a filter that we had before, and here this is a true means that we iterate twice. So it's a lot of code to actually express the same thing that we just expressed in the code file. And another problem that we have here is typically these graphs are not homogeneous like this one. So we have different kinds of processes, different kinds of actions. So for example, we have clans, and we have the hobbits, for example, and we have not only the hate relationship, we have the clan leader, and the node relationship between the hobbits, for example. And now the analyst would ask something like, which two clan leaders hate each other, and one of them knows photo over 1 to 10 hops. So that's also a typical question. Let's look at this, how we would say this in Cypher. So this would be the query. So this would be the query. So we have a clan, we have a leader of this clan. This leader hates another org, which is also a clan leader, and the other clan leader knows photo in 1 to 10 hops. So we have some predicates here. Okay, how would you express this on a graph processing framework? You can try it, but no. So that's kind of our motivation. So we want to make graph queries, or graph queries especially, usable on those kind of frameworks. So distributed data flow frameworks like ApacheFlink, or for example ApacheSpark. So, but to be honest, of course, each of those systems has a specific use case, or there are strong points. So we have here 2 dimensions. It's more complex than this, but for this talk it's enough. So we have the ease of use, which is like based on how easy is it to express a problem in a system. And we have data volume, so it's about scalability, using more machines to compute. So and on the one hand of the spectrum, you have graph databases, like for example ApacheFlink. So you have the declarative languages, easy to express a problem. You have visualization, a lot of tooling, community, and so on. And on the other end of this spectrum, you have graph processing systems. So the well-known one is Apache Giraffe, which is really dedicated to compute graph algorithms on a distributed cluster, so a shared nothing cluster, but only for this, nothing else. Then we have a bit more abstraction here. Those are the graph data flow systems. So like, for example, it's also a graph processing system, but on top of a data flow system like ApacheSpark or ApacheFlink, GraphX, for example, on Spark, Jelly on Flink. And now you see there's a free area in the right upper corner, and this is where we position our research project, which is called Gradoop, and where we want to combine the expressiveness of graph databases, not as much as graph databases, but a little bit less, but also the scalability. So that's kind of the goal of the project. And I will give you a short overview about the project before we dive into the Cypher implementation. So we built on the shared nothing cluster, like I already said. So we use Hadoop and HDFS. It's our data source, data sink. So that's where we store our graphs. We use ApacheFlink as a distributed operator execution layer. So this is where we implement actually our graph operators. And Gradoop itself is just a layer on top of ApacheFlink, which uses the batch API of ApacheFlink or the stream API. I will talk about this maybe later. And Gradoop, what it provides to you is an abstraction of property graphs on top of this data flow system. So this is a data model that we implement. I will talk about this on the next slides. And we provide a set of graph data flow operators. So one of them is, for example, pattern matching, which we will talk about in detail today. So, but for those who don't know what Flink is, on the website they quote, it's an open source streaming data flow engine, and it provides to you data distribution, communication, and fault tolerance. So all the hard parts of parallel and distributed programming are handled by this system. It does this really nice, especially for the streaming use case, but it also has a batch component, which we are currently building on.
So what are the basic abstractions that you have in ApacheFlink? So one is a data set. A data set is just a distributed collection of data objects like POJOs, so normal Java objects or tuples, things like that. And then you have transformations, and transformations are just operations on data sets to produce another data set, like for example map or reduce. So for example, we have a data set here, a transformation produces a new data set. And a data flow program is just a composition of those transformations. And this is the way how you program in these kind of systems. So you have to translate your problem into a data flow program using those abstractions that the data flow framework provides to you. So what Flink does for you is the parallelization. So it scales out the computation and the data to multiple machines, computes it, and gives you a result. So what are those abstractions? I guess it's a bit small here. It's just categorized in, so this is Flink dataset transformations, unary, so which means one dataset as input, and binary, two datasets. And you have the common suspects like map and reduce, and these SQL-like things like filter, group by, blah, blah, blah. And we have the binary stuff like join, for example, union, co-group. And there are special operators for iterations, so like delta iteration or bulk iteration, which allow you to express iterative algorithms, and most graph algorithms and machine learning algorithms are iterative, to express on this framework. We also use it. So Gradoop, on the other hand, like I already said, is an abstraction on top of ApacheFlink, which provides you not the dataset API, you have it underneath, but it provides you already a property graph abstraction on top of Flink, plus several operators. So the basic data model that we have is a property graph. So we have vertices and directed edges, and we have this concept of so-called logical graphs. So we have not only one graph, but you can have multiple graphs inside your database, which can also overlap. And the concept here is that these graphs are also first-class citizens like vertices and edges, and they can be input and output of operators, of transformations. So this is why they have also identifiers, so they are uniquely identified in the system. You have type labels, maybe you can't read it, but it's like this is an org, this is a clan, this is an area they live in, it's Mordor, so it has attributes. And here we have the hobbits. So we have attributes everywhere and labels. And you can just load this into the system. The abstraction is already there. You don't have to care about how this is mapped to the underlying dataset API. So this is what Gradoop provides you from the data model point of view. And it's called the extended property graph model because of these logical graphs that you have additionally to the regular property graph model, like in Neo4j, for example. So in transformations that we provide are not based on data sets, but on logical graphs as input, so a single graph or a collection of graphs as input. We also have unary and binary operators. So for example, what we have here is pattern matching, which we will focus on today. And other things like grouping, it's an OLAP, graph OLAP operator, subgraph, for example. Binary operations, for example, to combine two graphs to a new graph, or to compute the overlap between two graphs, or the exclusion. Also, graph collection operators, they are kind of relational. So you have a collection of a large collection of graphs, and you want to, for example, filter them, so by a predicate, like selection in relational algebra, or also pattern matching on each of these graphs. And there are also these set theoretical operators like union of collections or intersection, difference, and so on. So I want to give you just two examples how these graph data flows look like using the subgraph operator. So the input here is a logical graph. We have different kinds of labels. So the colors are the labels on these vertices and edges. And what you do as a programmer, you just say, okay, I have my logical graph. I load it from HDFS. It's just a method here, but there's a bit more happening. And you say something, okay, my graph.subgraph, and then you give two predicates, so it's two lambdas, which are just filtering functions for vertices and edges. So what we say here is a vertex is in the output graph if it has a green label, and an edge is in the output graph if it has an orange label. And of course, both source and target vertex of the edge have to be fulfill this vertex predicate. So in this example, the result would look like this. We have only those vertices that are that fulfill the predicates, and the edges between them that fulfill the predicates. So in the output is again a logical graph, which again can be input for another operator. So this is the data flow on the graph level. That's what Gradoop gives you. And what it also gives you is pattern matching. So you have again a logical graph as input. Then you define a pattern. So for example, we are looking for subgraphs that start from a green vertex with an orange edge to an orange vertex. And then you have just a graph here. You say match. You define a Cypher pattern. It's just green, orange, orange. And then the result is a graph collection in that case, which contains all the subgraphs that match this pattern. And the subgraphs are, of course, subgraphs of this input graph. So this is from a high-level point of view how Gradoop works. And now we will focus on really pattern matching, so how we do this. Because it's just an example operator, we have multiple operators, but this is a very interesting one. So I will give you an overview, and then Max will give you more details about the implementation. So the steps are really similar to every query processing system. So you have the queries. This is the query from the beginning. We pass the query at first. So we've written our own ANTLR grammar. We could switch to OpenCypher. The problem here is that OpenCypher doesn't support the extended property graph model, but it's just an implementation detail. So then we translate this into object representation of this query. We translate the predicates to conjunctive normal form because it's easier to evaluate them in that case. Then we use statistics about, for example, how many red labels are in the search graph, how many blue edges are in the search graph. There are more statistics, and then we use this. We build a coast-based greedy optimizer that takes the query, this representation, the statistics, and produces a query plan. And then using this query plan, every node represents a physical operator which maps again to Flink transformations. And the output, if you execute this, is then the collection of found patterns in the graph. And now Max will tell you a bit more about what's happening after this part. So we now have generated this plan, and then we execute this. Okay.
Yes. So as Martin said, after we have parsed and planned the query, we end up with something like this. This is the query plan for this particular query. And just to give you a short overview of what this actually means. So this is actually a tree. Maybe it doesn't look like this in this kind of visualization. But to execute it, we basically start with the leaf node. So for example, we want to find all relationships that match this sub-pattern. So we want to find all relationships that have the type heights. And so what we basically do is we filter and project the collection of all relationships we have in our graph. And after we've done this for all atomic patterns, we start kind of building up larger patterns, and we do this by joining. So, for example, to get this sub-pattern, we join all nodes with the label or with label org together with all relationships with type heights. And so we continuously build up larger patterns by joining together smaller patterns. In the end, this is, for example, this is the last operator in this plan. We do a filter step where we filter out all non-valid results according to a given predicate, which is in this case making sure that org1 and org2 aren't the same and clan1 and clan2 aren't the same. So we throw away all embeddings that don't, or all results that don't hold for this pattern. A slightly special operator is the expand embedding operator. This is a traversal operator. So in this operator, you don't only expand one hop, but you can expand multiple hops using one operator. This is the star thing you see or might not see over here. So in this case, we specify we want to step at least or do at least one hop, but at most 10. Yes. And just to walk you through some or how this works internally and how this maps to Flink. Every of these operators produces results, intermediate results or the end result, of course. And so what we did is we implemented we have two main data structures. For once, this is the embedding. The embedding stores one particular intermediate result or the end result. So it has three types of entries. One is the list of ID entries. This stores the mapping of actual nodes or vertices in our graph to nodes or edges in the query graph. Then we have a list of properties. So every node, as you know, in the extended property graph model, every node and edge, and even graphs, but that's not relevant here, have properties like names, or like Frodo has a name, or like every hobbit has a name. And we store this in a separate list. And then we have paths. This is just an implementation detail to make sure that if we do this variable length expand, that we always end up with embeddings of the same size or with the same amount of entries. But it's not too important for now. To say, these embeddings, they are kind of dumb. They don't know, they only store things, but they don't know what they actually store. And to make sure we have a mapping, or we actually store this knowledge as well, we have also embedding metadata. The reason we splitted these things is that since we are in a distributed environment, we eventually have to send data over the network. This happens usually when we do a join, and that's quite expensive compared to just accessing RAM or something like this. And so we have to make sure that our data structures we actually send over network are as small as possible. And since this metadata information is the same for every intermediate result for every step, we can just have one metadata object for every node in the query plan. And this basically stores the mapping of which variable in our query graph maps to which entry in the embedding. And the same goes for properties. So to have some examples how this actually works under the hood. So we have 3 layers here. This is like our example layer. This is the actually data we have, our orgs. Then we have a more or less relational view. So kind of what we do on internally is we map things to relations. And then you have the same thing as the Flink view, or how our physical operators in the end map to Flink operators. So this is an example for a leaf node. So we want to find all nodes that are a hobbit and have the name Frodo Baggins. So we scan through all our nodes in the graph, filter out these nodes which have the according label and the according name. And what we end up is with a couple of, or maybe just one node and all its properties. And this can, in a relational view, this would be a table with the ID and the properties of every hobbit named Frodo Baggins. And as a follow-up step, we do a project step because we want to again save some data size. We throw away all properties we don't need anymore, because why would we carry them if we never access them again? In this case, we are not really interested in any property of Frodo, so we throw out everything. In Flink, this maps to a flat map function. Flat map allows us to combine these 2 steps into one. This is some internal thing of Flink, why that's better. Instead, we could also do a map or a filter and a follow-up map step, but this would cost us more, would need more time. So flat map is basically you have input, you have one vertex, or in this case a vertex, and you can output 1 or 0 or even more, but no, that's not the case for us. You can output a variable amount of results, basically. So this is leaf node operator that projects and filter embeddings or vertices. This is always the start operator in a query plan. Then you have the maybe most important operator is the join. So this is to join the sub patterns to larger patterns. So for example, you have this pattern, you have the org, which is as related to a clan, and you have an org which hates another org, and you basically want to join this together to become a larger pattern. In relational view, this is the same as for relational databases. So you have 2 tables basically. In our case, it's 2 intermediate results, and you join them together. We can't only just join them because we have some constraints. This is due to how graph databases work. You have to basically check that you don't assign the same node or the same relationship to different nodes in your query graph. So you don't want to be this org and this org to be the same. Or you don't want this relationship and this relationship. In this case, they would never be the same, but in other cases, they could be the same. You don't want to traverse the same relationship twice. at least depending on your settings, but that's out of scope for this talk maybe. And so we take those two subgraphs and join them together and get one larger graph. You can see that in the example we don't store this node twice, because why would we? Would be a waste of space. And again, this maps to this time a flat join. It's not a flat map, because as I just said, some intermediate results wouldn't be valid under the assumption of isomorphism, or this relationship or node uniqueness. So maybe the most interesting operator is the variable length expand. This is basically, in our example, would be we have an org and we want to find Frodo Baggins and in 1 to 10 steps. And for this, what we do is we use a iterative expand. Under the hood, this is basically just a iterative join with some, you can do some optimizations which hopefully help you making it faster. So what we do is we have the left side, which is only the org, and then we have a set of node relationships and their nodes, and then we kind of join them iteratively and yield every possible result, of course, if it's longer than 1 hop and shorter than 10 hops. So it's not that we only yield the largest result, but we yield all intermediate results as well. This is what Martin mentioned before. Here we use the bulk iteration. This is kind of a cool thing for your streaming processing systems. Spark, for example, doesn't have a iterative operator. Flink does. And so we use this iteration operator to iterate over the graph and produce our results. And as a last step, we would do filtering. So we had this predicate that org1 and org2 are not allowed to be the same. So obviously we have to filter out this result, and that's quite straightforward. And this maps to the filter operator, which is already present in Flink. So that's quite straightforward. That's basically the operators we have implemented so far, and which allow us to run most Cypher queries right now. What we don't have at the moment is a return statement. This is kind of work in progress, but we will eventually have it. And there is some caveats on how to map the projected results to a graph again. That's why we don't have it right now. And what we also don't have is aggregation. But you can do aggregation by just adding, Gradoop itself has operators for aggregation. So what you could do is you do the pattern matching without aggregation and do the aggregation as a follow-up. So, but most of the rest of the Cypher standard we support right now. So, now that we have planned our query, this is what we end up with for Flink. So this is the visualization of what Flink generates. So we have our query plan, and then we translate it to a Flink query plan. And this is for this particular query. This would be the Flink query plan. You don't see much here. That's completely okay. We just wanted to show you that it's quite a lot of steps you have to take in order to produce the result. And this is just a more detailed view. So here you have basically your data source, then you do a set of filter and project, so you get all the vertices and edges you want to work with, and then you join them over and over, and in the end you end up with one data set which contains your results. And then you can, for example, write them into HDFS or wherever you want to store them. So yeah, what we want to do, what we would like to do, is that we want to integrate the Cypher technology compatibility toolkit. This is a set of cucumber tests which allow you, if you implement them, they tell you if you have implemented OpenCypher correctly, hopefully. We haven't really done any like broader checks now if what we produce is correct, so this should be perfect. We want to do benchmarking. We have some preliminary evaluations, but we should go into more detail for this, and for this we want to use the LDBC social network benchmark. This is a benchmark specifically designed for graph databases or graph systems. And we can do a couple of optimizations. So right now we use a greedy planner. We could use a dynamic programming planner, hopefully yielding better query plans and faster execution times. We want to improve our cost model. So in order to be able to produce a plan, you have to estimate how costly each step in the plan would be. Right now we have a very basic, very simple model based on probabilities, but this doesn't scale at least. Yeah, not really if you have this amount of joins. And yeah, you can do reuse of intermediate steps. So as you see, for every like org, we have 2 orgs in our pattern right now. For every org, we would filter the list of all nodes in our graph. But actually, that's the same. I mean, since we only filter for the label org, we yield the same result on both sides. So we could reuse it basically, which we don't do yet. And another problem in the distributed environment is partitioning. So if you have vertices which are with a high out degree or in degree, so in a social network, for example, people with many friends, they increase the computing time on the particular node which is in charge for handling this node. They increase the computing time unevenly to every other node in the cluster, for example, and so we have data skew, which means that some workers take way more time to process a result, to produce a result than other workers. And it's a hard thing to partition the nodes over the cluster evenly so that you end up with a even computing time. And yeah, of course, we want to support the rest of the Cypher features and maybe even introduce more Cypher features like regular path queries or support for this extended property graph model. And here's where you can come into the big picture, because we'd like to, if you are interested in this and if you think that's cool, then it's open source. So you can work on this with us together and yeah, just contribute if you like to and if you think that's a cool thing. Yes,
Cool.
Thank you.
Thank you.